Hello, everyone. So thank you for joining the International Day of Women in Statistics and Data Science Conference of 2025. This year's theme is Thriving in Your Environment. Just to note, we will be recording this event and the videos will be available on the Caucus for Women in Statistics YouTube channel. And we kindly request you to post any of your questions to the speakers in the Q&A chat given. So without further ado, we would like to invite our first speaker, Stina, who will be speaking in this first talk of the session, which is about her advancing statistical methods. Thank you. Stina.
Thank you, Rajenki. I hope everyone can see my screen.
Yes.
Yes, perfect. So today I will talk about alternative formulations of the allocation probability test statistic to enhance power in response adaptive clinical trials. And this is joint work together with David Robertson, Thomas Yaki, and Sofia Villar, who will talk at a later session today. So the purpose of many studies is to estimate the causal effect of a treatment on an outcome. And the gold standard is to do a randomized controlled trial, or an RCT. And a common way to allocate patients in an RCT is using equal randomization to the treatment arms. So in a two-arm trial with one experimental treatment and one control arm, half of the patients will be allocated to the experimental treatment arm and half of the patients to the control arm. However, this means that many patients in the trial will not receive the best treatment if a best treatment exists. An alternative that potentially can increase the patient benefit within the trial is using a response adaptive randomization, or a RAR. And in a RAR design, the allocation probabilities to the different treatment arms are updated throughout the trial, which means that a larger fraction of patients than in an RCT can receive the better treatment. And this figure here illustrates the RAR procedure. So you start by allocating some patients using equal randomization. And once the outcomes of these patients have been observed, the randomization probabilities are updated and the next batch of patients are allocated to treatments. Once their outcomes have been observed, the randomization probabilities are updated again, and so on, until all the patients have been allocated to treatment arms. And using a RAR procedure, this can end up in quite uneven sample sizes on the different treatment arms. However, when these allocation probabilities are updated, this means that data from the RAR design is dependent on each other and that the IID assumption that we usually make is not fulfilled. And thus, in most cases, standard inference and analysis methods are no longer applicable. And this can, for example, lead to inflated type 1 error rates, so too high probability to conclude that one treatment is better when they are actually the same, and decreased power in hypothesis testing, so it's a too low probability to conclude that one treatment is better when that is actually true. One solution that was recently proposed in these two publications on the bottom was to use a hypothesis test based on the allocation probabilities, called the original AP test. And this test just counts the number of times the allocation probabilities favor one treatment, because if one treatment is better, the allocation probabilities will, on average, show this. And this test has demonstrated good performance in some RAR settings. And in this work, we want to further investigate the properties of the AP test. So first, we want to try to change the formula of the test statistic to see if that increases the power or the probability to discover a better treatment. We want to compare it to traditional methods, and we want to make some practical recommendations. And this is the outline of the rest of the talk. So first I will present the notation and some assumptions, then go through the original probability test and the alternative definitions that we have looked at. I will present some results from a simulation study and finally draw some conclusions. So we considered a two-armed trial with binary outcome. So we have one experimental treatment and one control treatment. and the outcome is success or failure. And we use the Bayesian response adaptive randomization procedure, or the BRAR procedure. And we have a total of n subjects that are observed, including a burn-in period and T RAR blocks with B subjects in each block. And at each block, every subject is randomized to one of the two treatment arms. And these randomization probabilities depend on the history of selected treatments and outcomes, so how the previous patients in the trial had responded. And the allocation probabilities are the same for all subjects in the same block and are then updated for the next block. And the scheme is illustrated here in the figure on the right. And the main idea of the original AP test was that because allocation probabilities will on average favor the promising treatment arm, they will differ from 0.5 in the two-arm case. And the test statistic is just then that you count how many times the allocation probabilities to the experimental arm is bigger than 0.5. And the distribution of this test statistic and the critical value are easiest to find with simulations, although there is a rule of thumb that if the sample size is relatively small, the critical value is the number of blocks minus 1, so the largest critical value with a non-zero type 1 error rate. And this is a small example, so it's 40 patients in a fully sequential trial, so B is equal to 1, with 4 patients in the burn-in and critical value 35. And this ends up with a type 1 error of 13%, and in this alternative we have a power of 27%. So one question is then, does the original definition of the AP test give the most power, or is there an alternative functional form that gives more power? So can we change this indicator function to something else? And we have looked at several alternative definitions that use more information. So I both considered settings where we move away from the indicator function and the dichotomization of the allocation probabilities. And I also considered weighting the allocation probabilities in different ways. And we have looked at several different alternatives, but the one I will focus on today is this one on the bottom right, where we weight the allocation probabilities by the block number. So allocation probabilities for blocks later in the trial are given a higher weight, and we don't use the indicator function to dichotomize at 0.5, but use the values of the allocation probabilities directly. And we have evaluated these different tests in a simulation study. And as I said before, we consider a binary outcome in a two-arm setting. And we consider two different sets of success probabilities, one with the more common outcome and thus higher success probabilities, and one with the more rare outcome and the lower success probabilities. And we have a rather small sample size, n equals 40, to mimic a phase 2 study. And we have a block size 1, so it's a fully sequential trial, and the allocation probabilities are updated after every patient. And we have 4 patients in a burn-in period. And we only look at the original AP test and the time-direct AP test, and that is to quantify the maximum power gain that can be made due to changing the functional form. And we compare against the Fisher-Exact test for the BRAR design and the Fisher-Exact test for the equal randomization design. We compare power and type 1 error rate. And this figure here will show the power curves of the different tests. So on the x-axis, we have the underlying success probabilities for arm 1. And on the y-axis, it is the probability to reject the null hypothesis. So in this first point here, it's the type 1 error rate, and for the other points, it's the power. And this is the result for the Fisher-Exact test for the equal randomization. And in this dashed red curve, we have the results for the Fisher-Exact test for the BRAR design. The solid red line is the original AP test, and this pink dot dashed line is the time-direct AP test. And here we can see that the time-direct AP test has higher power than the original AP test. So the pink line lies above the solid red line. We also see that it has higher power than the Fisher-Exact test for the BRAR design. and that it has similar power as the Fisher exact test for the equal randomization design in some settings. So for the lower probabilities, the time-direct AP test is slightly higher, and for the higher success probabilities, it's slightly lower. It should also be noted that the time-direct AP test has a higher type 1 error rate than the two Fisher exact tests, but it's still restricted to the targeted 10%. And if we look at the other sets of success probabilities, so the one with the 0.1 for the null hypothesis, we see similar results. So the AP test, the time-direct AP test has higher power than the original AP test, and it also has higher power than the Fisher exact test for the BRAR and equal randomization design, although it still has the higher type 1 error rate. So to conclude, we have investigated the AP test for BRAR trials with 2 treatment arms and binary outcome. And we saw that the AP test can give power gains compared to standard non-Bayesian methods, but it depends on the study settings. We also saw that the functional form of the AP test is important, and in the investigated scenarios, the time-direct AP test performed best, although there were alternatives that performed quite similar. And in some cases, it actually provides similar power as an equal randomization design, but with the increased patient benefit. And the practical recommendations that we can make is that the more continuous versions of the AP test works better. The AP test performs relatively better in a trial with a small sample size, and that the more aggressive design gives a larger advantage. But more investigations are needed, and this is we are currently working on this. And these are the main references. Thank you very much for listening.
Thank you, Stina, for the great talk. Any questions, please post it in the Q&A chat. So before we have any questions, Stina, can I ask you, so you considered binary outcomes. So does the AP test work for non-binary outcomes?
Yes, because the test statistic is only based on the allocation probabilities. The test will work for any type of outcome as long as you can calculate allocation probabilities.
Okay. I did see a hand being raised, but could you please post the question in the Q&A chat? I'll just take a look if there's anything. Stina, are you able to see the question answer chat yourself? If not, then I'll read it out. So Pamela asks, now you are using WT equals to T identity. Have you tried any different way?
That is a very good question. We have tried using the rank number as a weight, which performed similar as using T, and we have discussed using, for example, the square root of T or other functions of the block number, but we have not looked at that yet, but it is a good point. Thank you.
Okay, thank you very much, Stina. We'll stop here. Although if there are more questions, please feel free to post here, and I believe Stina will be able to answer directly. Thank you so much.
Thank you.
So the next speaker for this session on advanced methods in health research is another postdoc from MRC Biostatistics Unit, University of Cambridge. Janne, please feel free to start whenever you are ready.
Can you see my slides? Can you hear me?
Yes.
Okay, great. Thank you very much for having me here. Thank you for letting me talk about my project on multivariable Mendelian randomization in a stratified setting. This is an ongoing project together with colleagues at the BSU, with Marco Palmer, Jessica Barrett, and Stephen Burgess. It's more an applied project compared to what you just heard in Stina's talk. So,
Janne, could you please just speak up a little bit louder? You're quite quiet for us to hear.
yeah, I can try to talk louder. I'm sorry, I don't know how to increase the voice here. Is it better now?
A little bit better. Just try to get as close to your microphone as you can. Thank you.
Maybe I can. Okay, but is it better now?
Yes, let's try that. Thank you.
Sorry for that problem. Next time I will test this more thoroughly in the beginning. So what I wanted to say is, can I move my slides? Yes. So I wanted to begin with a more applied project, like it's applied stuff. Hate this. So coronary artery disease had a lot of risk factors. Some of them you can modify and others you can't modify in the traditional way. And in this project, I will not focus on all those risk factors. I would just focus on the cholesterol levels because they are usually available in longitudinal data in electronic health records. And that's kind of making them interesting to study just because there's so much information available in a more observational study style. And I will also focus on age and gender, more specifically sex, just to define my menopause. And I will need genetic factors because this is a Mendelian randomization and we need genetics to do this randomization. Now, why is cholesterol such an interesting marker or biomarker for testing menopausal effects? That's because it changes with time. So if you look at younger women who are in their reproductive age, they typically have lower levels compared to their age-matched men. But when you look over time, there's an increase. And with menopause, it's actually ending up that women have higher levels of cholesterol. And that's the risk factor here, right? So if they have, like with menopause, higher levels, then their risk for cardiovascular disease will increase too. And the question is, how can we analyze this in a Mendelian randomization setting with this time variable effects that we assume to have here? This leads to my two questions that I wanted to talk about here. The first is simply, can we find genetic effects that affect the cholesterol levels and probably have an interaction with age, sex, and or the menopausal status? And if we find those different genetic effects, can we then use them in a causal framework of Mendelian randomization and test for sex, age, or menopausal specific causal effects? For those of you who don't know Mendelian randomization by heart, this is kind of the simple overview of what we are doing in Mendelian randomization. We use genetic markers, genetic variants, as instruments to estimate or to proxy the risk factor that we're interested in. In our case, it's total cholesterol levels. We assume that we have this nice, strong effect. This is a valid, so that our genetic instrument is a valid predictor of our risk factor. And there are two more assumptions that we need. We need to assume that any confounder of X and Y, of the exposure and the outcome, are independent or do not influence our genetic instrument, and that the effect that we might observe on the outcome from the SNP, that's completely mediated by X. So there's no direct path from our genetic marker to the outcome. Why do we need those assumptions? Because then our causal estimator that we are looking for, our causal effect, that's simply the ratio of the two genetic effects on the outcome and that genetic effect on the exposure. And this is great because those SNP effects, they're typically available in GWAS databases like GWAS catalog. So we don't need to run any expensive clinical trial. We just can use those publicly available data. Now, in my example, I wanted to look at cholesterol and coronary artery disease, and sex, age, and menopause are potential confounders. And the question is, does the second assumption still hold? You would assume that the genetic marker doesn't change, but the SNP effect actually might change because you have different hormone levels, you have different levels of gene expression and genetic regulation, and that also might change over time. Like a lot of things change with menopause, and some genes might actually be silenced, so the genetic effect might differ with time. And given all those potential interactions, I was thinking maybe a longitudinal model might be better for this kind of analysis. And this is my proposed framework. I wanted to use longitudinal cholesterol data and estimate in this longitudinal GWAS model the SNP effect on the mean level, on the slope, on the trajectory of the cholesterol levels, and also on the variability, like how much is the variance within a person over the observed time. And then I simply plug them back into a multivariable MR framework. So we use those 3 estimates for the same SNP, use them on those 3 different types of the exposure, the mean level, the slope, and the variability, and then estimate those 3 independent causal effects, test if there are 3 independent causal effects on our outcome of interest. I did this using the UK Biobank data. So this is baseline and GP data set, electronic health records from like the last 20 to 40 years, depending on the samples. I restricted my analysis on white British ancestry because the Mendelian randomization needs the same ancestry in the exposure and outcome data set. And my coronary artery disease data was only available in Europeans. I excluded anyone with a pairwise kinship, so like mother-daughters pairs or siblings, because the longitudinal model doesn't really allow for correcting for that. And I had at least 3 data points per individual just to allow some variability estimation. If you just have 1 time point or 2, it's really hard to estimate a variability there. And then I defined strata for the young people, so that's premenopausal women or just young men, and postmenopausal women and older men. And I decided to use for the older people everything that was observed in the GP dataset after the UK baseline. And for the younger ones, I used everything before baseline, just because my menopause information is just given at baseline. And running my longitudinal GWAS, everything looked really good. Even with my relative small sample size for the stratified data sets, I found enough instruments to do the MVMR later on. And I found a lot of interactions between the strata. So there were significant sex interactions and significant age interactions. So the genetic effect differs depending on which strata you're looking at. So now I tested, like, can we actually use them in the MVMR context? And this is the MVMR per strata. So I tested in elder men the mean level of cholesterol and the variability of cholesterol on the risk of coronary artery disease and so on for each strata. And as you can see, we find always a significant effect of the mean, which is kind of good because this is our positive control, right? This is nothing new. We know that cholesterol should affect coronary artery disease, and indeed we can find this. But we also have a second finding, which is a significant effect of the variability, but only in younger men. And I will discuss this in a moment. I then went on to do a different approach. I combined again the age groups, but kept the sex separate. So I combined the 2 age groups for men and the 2 groups for women, and now tested if there's a conditional effect. So it's the effect of the mean or variability conditional that there is an age effect. And for the men, we don't see any changes. So the effect sizes changes a little bit, but we still find those 3 significant effects as before. But in women, we lose the effect of the premenopausal women of the mean level on the coronary artery diseases, which means that premenopausal women do not have the high levels of cholesterol in premenopausal women do not pose an increased risk for coronary artery disease. This risk only starts after menopause, which is in line with everything we know from other studies. And with this, I would like to sum up. So I successfully replicated with my longitudinal approach the mean levels having a causal effect on the coronary artery disease risk in each strata. And when I tested for the menopause dependency, I could see that there is no longer an effect in premenopausal women. So there is a true menopause effect. We observed an interesting effect of the variability, which is contrary to the literature, because literature always says that higher variability is associated with higher risk. But this might be due to our UKB data set. We don't have healthy assessments. We have assessments from people who are sick enough to go to their GP, and that might actually bias our observation. And in this case, it means people are going to their doctors, they're getting more measurements, they're getting the statins, so lipid-lowering medication, and that actually might prevent cardiovascular disease risk. So it might make sense why we see this negative effect and not a positive effect. And that's why we want to replicate our finding in the interval study. That's a study of healthy blood donors here in Cambridge. We hope with changing to this healthier data set, we might better understand the variability effect. And this I'm done. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Janne, for the interesting talk. Any questions, please post it in the Q&A chat. I'll just go ahead. Janne, so what did you mean by variability here? And does the presence of genetic allele affect the variability of a trait?
That's a very good question. Variability in the genetics is assumed to mean that there's an unobserved interaction between the genetic and a confounder. And it actually could mean in our MR framework that by including the variability, we are adjusting for every potential violation of this. The instrument has to be independent of the confounders. So it's really necessary to look like those hits you find for variability. Are they indeed interactions with inactivity or with alcohol consumption? So variability really means in this case, there is something going on that's not just genetic, but probably an interaction with the environment and other unobserved effects. Yes, was that? Hope that.
Thank you. Thank you, Janne. So this is me, Rajenki Das. Thank you everyone for joining. Thanks to the speakers, Dr. Stina Zetterstrom and Dr. Janne Pott. Thank you to MRC BSU for sponsoring. Thanks a lot to the organizers and attendees and everyone else. Thank you very much, and I hope you enjoy the rest of the day.